Okay, so 7.5. We're skipping 7.4. 7.5, we're looking at exponential functions. We've already kind of talked about exponential functions a little bit. Exponential function, all that is your variable is the exponent. That's all I mean when I say exponential function. Don't freak out, because it looks weird, because you've never seen that word exponential. All I mean when I say an exponential function is the variable is the exponent. We've dealt with them on the warm-ups. 5 to the x power, 2 to the x power, -4 to the x power. All an exponential function is my variable is the exponent, is an exponent now. Okay? So as I look at some of these, let's go ahead, a couple of things to remember. The parent function looks like this. So the parent function for an exponential function looks like AB to the x power. So AB to the x power. And we're going to deal with this more tomorrow, but this is what the parent function looks like. A and B are just going to be numbers. Okay? So A and B are numbers. So as I'm looking at this, we're going to have A times B to the x power. This is exponential because my variable x is the exponent. A and B, even though those are variables, those are just going to be numbers when we actually deal with them. So some examples of exponential functions. Y equals 2 to the x power, something like that. Okay, y equals, I don't know, 4 to the x plus 1 would be another example of an exponential function. Okay, so these are all examples of an exponential function. Now, as I look at graphing these, they're going to look at different. They're going to look at a couple different ways. They're either going to look like this. So here's kind of what my graph of exponential functions look like. Now, don't make this harder than it is. When I graphed a linear equation, I got a line. When I graph an exponential equation, I'm going to get this curve. Okay? Now, usually, they're going to go through 0, 1. Now, sometimes they won't, but usually they're going to go through 0, 1. Okay? Now, it might be flipped, so you might either see it like that, or you might see it going downhill like this. And we'll talk tomorrow about how you kind of tell whether it's going to go curve up like this or curve down like this. Now, there's always an asymptote, and we'll explain what an asymptote means. There's always a horizontal asymptote across the bottom. And that's going to be y equals 0. So the line y equals 0 is a horizontal asymptote, and you're going to see asymptotes as dashed lines. And you'll talk about asymptotes. We're not going to talk about them a ton in this class, but all an asymptote means it's a kind of an imaginary line that my graph gets closer and closer to without actually crossing it. Okay? So what this says is I have a horizontal line, horizontal asymptote, that my graph gets closer and closer to without actually touching it. Okay? Let's go ahead and look at some graphs. Okay? How we're going to do a graph is we're going to make a table. That's how we're going to graph exponential functions. Okay? When you get to Algebra 2, you're going to talk about other ways to graph exponential functions, but for today, all you're going to do is make a graph. You're doing exactly like we did on the warm-ups. Basically, all you're doing is plugging numbers into your calculator. So let's go ahead and look at example 2. We're going to skip example 1 for now. Let's look at example 2. Y equals 7 to the x power. Just by looking at this, why is this an exponential function? Okay, my x is the variable. Well, more specific. Something with the variable. Why is this an exponential function? Okay, more specific. The x is the what? Exponent. The variable is the exponent. Anytime the variable is the exponent, this is an exponential function. So in the back of my mind, I'm thinking it's going to have a shape like this. My graph should end up having some shape like this. Okay? So let's go ahead and look at this. So we're going to make a table. And these are the 5 numbers I want you to use. -2, -1, 0, 1, and 2. So every time we graph these are the 5 numbers I want you to use. Now, we'll worry about the y-intercept and domain and range later, in a second. But all we're going to do is we're going to plug this in our calculator, just like we did on the warm-ups. That is why I did them on the warm-ups with you, so you could get practice plugging them in your calculator. So we're going to plug in our calculator 7 to the negative second. Now, when you do negative, make sure that you do not use the minus symbol, that you use the negative symbol that's left of the equal sign. So it should look something like this. 7 to the negative second. That's how you plug it in your calculator. If you're not doing this, please do it. So when you get to the homework, you know how to do this. So 7 to the negative second, 0.0204. Just round out 4 is fine. So 0.0204. If you're not getting this, please let me know. So that's all you're doing when you're going to make your table, is you're plugging them in just like we did on the warm-ups. 7 to the negative first. So 7 to the negative first. What do we get? 0.1429. Yep, 0.1429. If I plug in 0, you don't really have to plug it in your calculator. Anything to the 0 power is what? 1. So it's just going to be a 1. The next ones you might not have to plug in your calculator. 7 to the first power, 7 to the second power, 49. That's all you do. To make your table, you plug it in like we did on the warm-ups. Don't make it harder than it needs to be. Now let's go ahead and graph these. All I give you is now you have 5 ordered pairs, so plug them in or graph them on your chart. Now your graph, you might have to get a little creative, and I'm not going to be super picky about the graph being perfect, but I should see that curve because it's an exponential function. So negative 2.024, which is going to be really, really close to 0. So as I graph that here, if I graph negative 2.0204, you go left 2, and it's just a little bit over 0. Because it's just barely over 0. Negative 1.1429. Now it's still going to be close, but I know 0.1429 is going to be what compared to 0.0204. If I graph 0.1429, it's going to be what compared to the other one? I love not being answered. That makes me feel great. 0.0204. When I graph 0.1429, that's going to be what compared to 0.0204? Just a little bit higher. That's all I'm asking for. Negative 1.04. It doesn't have to be perfect, because my graph is going to look weird, but it's going to be a little bit higher. So I'm not going to be too picky about, this looks like a 0.5, so I'm going to take points off. No, I don't really care. It just needs to be a little bit higher. 0, 1 is here. 1, 7. 1, 2, 3, 4, 5, 6, 7. And 2, 49. And this is what I kind of mean about it's going to be off the graph. So 249, I don't really care where you put it. It's just going to be somewhere up here. So like I said, it doesn't have to be absolutely perfect. It might be a little off over here or whatever. Okay, but 249 is going to be somewhere off the page or off the graph. And just graph it somewhere. Now, like I said, the exponential graph looks something like this. You're going to have a curve like this. Now, one of the trademarks of an exponential function is it grows really, really quickly. And you should see that on your graph. Because I go from 1 to 7 and then 2 all the way up to 49. So an exponential function either increases really quickly or decreases really quickly. That's one of the characteristics. Okay, any questions on graphing this? All of you guys can do this. It's plugging in points and graphing ordered pairs. Now, make sure you answer the question. I want to know the y-intercept. So if I want to know the y-intercept, you can either look at your table or look at your graph. Where does this cross the y-axis at? 1. You can look where x is 0, so look at your graph. The y-intercept is 1, or look at your graph. It crosses at 1. Now I want the domain and range. This is going to be a little tricky. Domain and range. You guys can do this. We've done this before. If I talk about domain, domain goes with what values? Good. Domain goes with x. So when I look at my graph, I want to know what x values does this graph exist for. So x goes horizontally. So I'm going to look from left to right. So as I go from left to right, what do I notice on the ends of this graph? They're what? What are on the ends of these graphs? Arrows, which means they do what? Go on forever. So if I look here, do I have any starting x value on the left? If I have an arrow here, that means I go on forever. So it's just going to keep on going, going, going. I also have an arrow over here at the top, which means it's going to keep on going, 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 going. So my domain is going to be all reals. What that means is that graph exists for all x values. It keeps on going. There's no ending point to the left and there's no ending point on the right. So it's going to be all real numbers. We're looking at x values, so left to right, the horizontal axis. Now the range is dealing with what values? Y. So to look for the range, I'm going to go from the bottom to the top because I'm looking at the y values. So I'm looking at my vertical axis, the y-axis. So I start at the bottom and the top. Now let's think about this. What y values can't exist? Say that louder. Why not? Yeah. No negative y values can exist. It cannot. My exponential graph does not go below the axis. Remember, I have an asymptote here. So that means that it cannot go below the x-axis. So I can't have any negative y value. So I know y has to be greater than what? 0. Can it be equal to 0? Can it ever touch this asymptote at y equals 0? I said it earlier. Can it ever touch the asymptote? If I look back up here, can it ever touch the asymptote? What did I tell you an asymptote means? Can it ever touch 0? No, so it's just greater than 0. So my y values are greater than 0 or positive values. So that's how you do the domain and range. Okay, any questions on that? Okay, let's look at example 2 right underneath it. Now, using the graphs above, I want to approximate the given value. So what I want to look at is I want to say what is 7 to the 0.5. You could plug this in your calculator. Look at your graph. 0.5 is the exponent, so that's my x value. So what I'm looking for is I want to know what is the y value when my x value is 0.5. So look at your graph real quick. When my x value is 0.5, look at your graph. I look at 0.5, I follow it up. What does it look like my y value is when x is 0.5? My x value. So I go to where x is 0.5. What is my y value when x is 0.5? Follow it up. What does it look like my y value is when x is 0.5? 3. So I would say 3. Now if you plug that in your calculator real quick, let's see how close we got. What is 7 to the 0.5 power? 2.6, whatever, close enough. It's not going to be perfect. We're going to estimate, approximate. So that is 3. So you're going to go to where x value is 0.5, follow it up to find what the y value looks like. It's going to be an estimate. It's not going to be perfect. Okay, any questions on that so far? Okay, let's look at a couple more. Let's go ahead and look at example 4 real quick. I'm skipping around. Let's look at example 4. Okay, if I want to graph this, we are going to make a chart, make a table. So -2, -1, 0, 1, and 2. Always start with those 5 x values when you're doing exponential. -2, -1, 0, 1, and 2. Now I want to know the y values. So let's start plugging them into your calculators. A couple ways you can do this. First of all, we notice we have parentheses. So look up here, plug this into your calculator as I do it so you can see it. It's going to be parenthesis. Now how do I put a fraction in? You can use the fraction bar if you want to. I always just use what? What operation means the same as fraction? Division. So 1 divided by 2, parenthesis. So that's my 1/2. And I want to raise it to what power first? -2. So what I always like to do, plug it in like this. I always like to find this answer and then subtract 1 from it because I have the -1 at the end. So I like doing this part first and then subtracting 1 from the answer. So press enter. That's 4. Now let me give you a shortcut. If I want to subtract 1, if you just put a -1, it'll automatically say, okay, I'm going to pull the answer that you just got and then subtract 1 from it. So if you just type in -1, that's just going to give you your answer -1. So 4 minus 1, or 3. So -2, 3. Okay. Now I do the same thing with the -1 and see what you get. So parenthesis 1 divided by 2 to the negative first power. So it should look something like that. There's a glare on there, but that's okay. Something like that. Get an answer and then subtract 1. And we get 1. So -1, 1 is my next point. Now I don't need a calculator for the next one. What is 1/2 to the 0 power? What was that again? You were yawning, I think. 1. 1 minus 1? 0. So some of these you don't necessarily need a calculator. The negative exponents I would always use a calculator. The positive ones you might not need to. What is 1/2 to the first power? 0.5, or 1/2. What is 0.5 minus 1? Negative 0.5, or -1/2. You can do decimal or fraction, I don't really care. Now let's do a 2. I'm going to use the calculator for this one. 1/2 to the second power. So 1/2 to the second power, 0.25, and then minus 1, -0.75. You can just use decimals. I'm not going to be picky. If you want to do fractions or decimals, I don't really care. So if I graph this real quick, let's do -2, 3. So -2, 1, 2, 3, right there. -1, 1, right there. 0, 0, right there. 1, -0.5, right there. And 2, -7.5, or -0.75, it will be a little bit below it. So there's my graph. Now let's think about this. I always have a horizontal asymptote. Where does it look like my horizontal asymptote is at? Instead of y equals 0, what does it look like my points are approaching? Y equals what? -1. So my asymptote is now here at -1. So if you get a complicated exponential equation, sometimes you can kind of look at your points to see what line is it approaching. It's approaching y equals -1. So if I draw my graph, like I said, an exponential can also be going downhill like this. It's going to look something like that. It's fine. Some are going uphill, some are going downhill. We'll talk Friday about how to tell which is which. So you're going to have the curve. Either way, you're going to have the curve. Okay, let's answer these questions. What is the y-intercept? Either look at your table or look at your graph. Where does this curve cross the y-axis at? 0. Look at my domain. Domain is x, so I move left to right. If I go left to right, do I have any specific ending or starting values for x? If I have the arrows, that means it keeps on going. So I don't have any starting or ending, so it's going to be all reals. Now I will tell you, usually your domain will be all reals, because you're going to have the arrows, which means it's going to keep on going forever. Now range, let's look at my range. Range goes with the y values. So I start from the bottom and go up. What is the smallest y, what's the first y value I start at? If I work my way, start at the bottom and go up, I start what? Y has to be greater than what? If my asymptote is at -1, I know my y values have to be greater than what? -1. They cannot be equal to -1 because that is an asymptote, so they can never touch -1, but I know my y values have to be greater than -1. Okay, any questions on that? Those are by far take the longest out of any of these. Are we good with plotting points? Are we good with, yes? We got this? Okay. Let's look at the next one. Let's look at a couple story problems. The consumption of soda has increased each year since 2000. The function c equals 179 and then 1.029 to the t power models the amount of soda consumed in the world, where c is the amount consumed in billions of liters and t is the number of years since 2000. We're going to not do part A. We're not going to graph it. We're just going to look at part B. I want to know how much soda was consumed in 2005. Let's think about this. It's a story problem, so I always want to know what are they asking for. As I look at this story problem, what are they asking for? How much soda was consumed in 2005? If I'm looking for how much soda, what variable am I solving for? Read the story problem. What variable represented how much soda? So y'all should be reading the story problem and then figuring out what variable represented how much soda, or the amount of soda. C. The amount consumed. C. C is the amount consumed. So how much soda is my variable C? So I'm thinking in the back of my mind, if I want to know how much soda, I'm going to be solving this equation for C, just like we did on the homework Monday. And I want to know how much was consumed in 2005. So if I start with my equation, C equals 179, 1.029 to the t power. What's nice about this? If I want to solve for t, what's nice about this equation? Sorry, not t. If I want to find c, if I want to solve for c, what's nice about this equation? If I want to solve for c, what's nice about this equation? It's already c equals. It's actually easier than what we did Monday because I don't have to try to solve for a variable. It's already c equals. Now, I need to know time. What do they tell me about t? What does t represent? Or a little more specific. This is time, but t is the number of years since 2000. So if I want to know how much was consumed in 2005, what is t going to be? 5. So I plug 5 in for t, not 1.75, sorry. 179, 1.029 to the 5th power. Don't make this harder than it is. I know it's a story problem. I know these look confusing. I get it. But look for what they're looking for. If I give you 2005, then t is 5. So I plug 5 in for t. Now if I want to plug this in the calculator, order of operation, what do I do first? Multiplication or exponents? Exponent. So do 1.029 to the 5th. Do that first. So 1.029 to the 5th, get an answer, and I want to take that answer and multiply it by what? 179. So C equals 206.5, and you can just round to the thing. Now be careful, make sure that is in billions. Make sure you label it. Billions of liters. We got one last week that the I step that you're going to have to pass to graduate is going to make you label things. So get used to labeling things. 206.5 billions of liters, which is a lot of soda. Okay, any questions on that? Okay, let's look at another story problem real quick. A certain bacteria population doubles every 20 minutes. Beginning with 10 cells in a culture, the population can be represented by that function. B equals 10 times t to the 2 to the t power, where B is the number of bacteria cells and t is the time in 20-minute increments. How many will there be after 2 hours? It's a story problem. What are they asking for? Read it, figure out what they're asking for. So look for keywords. How many? How much? So what are they asking for? Okay, they don't specifically say it, but what do they mean? If I want to know how many will there be, I'm looking for how many what? Bacteria. And what variable represented bacteria? B. So I'm looking for B. That's what you always want to do with story problems. What are they asking for? That is the variable I'm trying to solve for. So I want to know B, and I want to know how many will there be after 2 hours. So if I start with my formula, B equals 10 times 2 to the t power. Once again, if I want to know B, this equation is already B equals, so that makes my life a little easier. Okay. What's T? T is time, but more specific. T is the time in what? T is the time in what? 20-minute increments. This is a little trickier. If T is the time in 20-minute increments, what time do they give me? I want to know how many after what? 2 hours. So how many minutes is 2 hours? 120. And T is the number of 20-minute increments. So how many 20-minute increments is in 120? How do I figure that out? Divide by 6, or divide by 20. So I want to know how many 20-minute increments are in 2 hours, or 120 minutes. So how many, so what is T going to be? If T is the number of 20-minute increments? 6. So T is 6. So be careful with what their time. They might try to confuse you and say T is the time in 20-minute increments. So that's going to be 6. If I plug this in my calculator, do 2 to the 6th times 10. 640. So 640 cells. Bacteria. You can put cells, is fine. Make sure you label it. Why does that make sense? How many did I start with? 10. And if it's doubling, it makes sense that I would have more than 10. Okay, any questions on those? Okay, example 7 real quick. These don't take very much work at all. I want to know, determine whether the set of data shown below displays exponential behavior. This is what you're looking for. Make a note of this. Your x value has to have adding by constant number. This is what I'm looking for. I'm looking for my x values to be increasing by a constant number each time. This is kind of clues to tell whether all I'm basically doing is giving you ordered pairs, like the table I made when I graphed earlier. Your x values have to be adding by a constant number each time. Your y values have to be multiplied by the same positive number. This is how you tell whether it's exponential. So your x values have to be going up by the same number each time, and your y values have to be multiplied by the same positive number each time. That's how you tell. So let's look at my x values. I go from 0 to 5 to 10 to 15 to 20 to 25. Am I adding or am I increasing by the same amount each time? Yes. My x values are adding by what? 5. X values, I'm adding 5 each time. So I'm good with my x values. That's what I'm checking for. The x values have to be going up by the same thing each time. My y values, I have to be multiplying by the same thing each time. So I go from 64 to 32 to 16 to 8 to 4 to 2. So what am I multiplying by each time for my y values? 0.5. So I'm multiplying by 0.5 or what? A half. So can someone go press the screen real quick? I'm multiplying by half. So your y values you have to be looking for, I have to be multiplying by the same positive number each time, which I am. I'm multiplying by half. 64 times a half gives me 32. 32 times a half gives me 16. 16 times a half gives me 8. So I'm multiplying by a half. That's what we check for. Okay? Now let's look at B real quick. My x values. What I noticed, the x values have to be adding by a constant number each time. What number am I adding each time? 3. So we're good with the x values. The y values, I have to be multiplying by a what? Positive number each time. So 12 to 16, 16 to 20, 20 to 24, 24, 28, 28, 32. What am I doing each time? Adding 4. I'm not multiplying by something each time. So that is no. Because I'm not multiplying by something, a positive number each time. I'm adding 4 each time. So A is yes, B is no. That's all there is to this. Just 2 things to look for. Any questions on that? Okay, homework. We have about 20 minutes. If you need to finish 410, then I would finish 410 because that's you today. I will admit. I know, we only about 15 minutes. Tomorrow you can. Okay, I gave you a worksheet for today just because you had the graphs and I thought it would make your life a little easier. You're graphing on your own. Yeah, let me explain this real quick. Okay, real quick, let me look at this. Look at this homework, worksheet 7.5. I can get out of here square for a second. Okay, 7.5, look at the worksheet. So, like I've said before, I try to be very, very intentional